other types of equations. There's a lot of material in this section, and not all of it's covered in a lot of detail. So let me know if you need more detail on some of this material that's presented. First equation we're going to look at are absolute value equations. The definition of an absolute value equation is that the absolute value of x is equal to x if x is positive, and it's equal to the opposite of x if x is negative. So what an absolute value does is make something positive. The absolute value of 3 is simply 3, because 3 is already a positive number, while the absolute value of negative 3 is the opposite of negative 3, giving us positive 3. So a couple examples where we've got some equations. It's simply the absolute value of x equals 5. X is either 5 or it's negative 5. Again, those are solutions to the equation, because if we were to substitute them back into the original problem, they would make the equation true. The absolute value of 5 is 5, and the absolute value of negative 5 is also 5. Threw in an extra example here. If you have the equation absolute value of x equals negative 3, there's no solution to this equation because there's no number whose absolute value is equal to a negative. And then a more classic example here, the absolute value of 3x subtract 1 equals 7. To solve this, what you want to do is remember that whatever's inside the absolute value is either equal to 7 or it's equal to the opposite of 7. So we can split this into two separate linear equations. 3x subtract 1 equals 7, and 3x subtract 1 equals negative 7. Either one or the other of these have to be true. Then we can solve each of the linear equations separately. We get x equals 8/3, and we get x equals negative 2. So there's two solutions to this absolute value equation. The important thing to remember is when solving these is the first step, set it equal to positive 7 and negative 7. You cannot simply solve the problem and tack a plus or minus onto the solution when you're done. That doesn't work. You have to do that as a first step. Okay. Next set of equations we're going to look at are polynomial equations. This is what's called a third-degree polynomial because the highest exponent is a 3. And we'll look at these in more detail in Chapter 4. This particular polynomial, notice that there is an x common to every single term. So we can factor an x out as the first step, and that leaves us with a quadratic. Factoring the quadratic, we now have x times x plus 3 times 2x subtract 1 equals 0. And we can set each of the three factors equal to 0 and solve each individually, giving us 3 solutions. Be careful not to forget the x. X equals 0 gives us one of our 3 solutions. And over here is just the long way to do the factoring using the AC method. Again, let me know if you need help with the factoring. Okay, the next type of equation are rational equations. Some of you may have nightmares about these from Math 95. They were one of the tough things in Math 95. What we needed to do for the rational equations, because they are fractional equations, is find the LCD. So the LCD for this one would be the x subtract 1 and the x plus 7. Multiplying every single term in the equation by the LCD, we can then actually reduce the equations, eliminating all the denominators. And once we've done that, it's a much nicer looking problem. We have 4 times x plus 7 times x subtract 1 equals 5 times x plus 7. And by the way, you probably noticed I changed the order here of the multiplication. It just looks prettier to have the monomial first, then the binomial. Then we can distribute, solve, get our solution. And do remember with the rational equations to watch out for extraneous solutions. Sometimes in the solving process we end up with a solution, a value for x that does not actually work in the original equation. In particular, you want to watch out for not to have a 0 in the denominator. Looking back at our original equation here, if either x equaled 1 or if x equaled negative 7, both of those values of x would make the function undefined. So if those had turned out to be solutions, they would not really be solutions, they would be extraneous solutions and would have to toss them. Okay, radical equations, you may have seen these before, but some of you probably haven't. The solving process is isolate the radical, and radical is just a word for square root. Once we get the square root by itself, we can square both sides of the equation. Sometimes we have to do this a second time. Solve, check, and again, watch out for extraneous solutions. Those sometimes show up in radical equations also. So for this example, in order to isolate the radical, we're first going to have to subtract the 1 to the other side of the equation, giving us x subtract 1 equals the square root of 11 plus x. Once we've isolated the radical, we can square both sides of the equation. So the right side simplifies because the square undoes the square root, leaving us just with the 11 plus x. But on the left side of the equation, because we're squaring the entire side, we're going to have to FOIL this out, and giving us x squared subtract 2x plus 1 equals 11 plus x. And again, then we can solve, factor, set each factor equal to 0. And that gives us two possible solutions, the 5 and the negative 2. But we need to check it in the original problem, and you have to be sure to go all the way back to the original problem, which had the square root in it. If we let x equal 5, it works out just fine, gives us a true statement. But if we let x equal negative 2, we get a false statement. We're ending up with negative 2 equals 1 plus square root of 9 is 3. That's not true. So x equals negative 2 does not work. There's only one solution, x equals 5. Okay. Variation on a radical equation, just a little bit different way to look at the same types of problems. Remember that a square root can also be written as x to the power of 1/2. And if you remember the properties of exponents, if you have an exponent raised to another exponent, you multiply the exponents together. So anytime you have an x to the power of 1/2, and then you raise it to the power of 2, 2 times 1/2 is just 1, and that eliminates the exponent. So by squaring, we eliminate the square root. And then the variation on that is, say if we have a power of 2/3. What we can do then is raise both sides to the 3/2. Again, as long as we're doing the same thing to both sides of the equation, we're okay. So using the reciprocal of the exponent, raise both sides to the reciprocal of the exponent. That cleans up the left side. 2/3 to the 3/2 is just to the power of 1, which is the same thing as not having an exponent, giving us just a plain 5 subtract x. The right side of the equation got a little more complicated, 4 to the power 3/2. To simplify that, you can think of it as square root of 4 cubed is 8, or you can punch it in your calculator. 4 to the power 3/2 will give you 8. And then we can solve and finish the problem. And then we've got variations on quadratic equations. These are equations that are quadratic in form. It doesn't look like a quadratic. As a quadratic, we have ax squared plus bx plus c equals 0. But what you'll notice here on this one is we have x to the 6th and then x to the 3rd. This exponent is exactly double this exponent. So we can factor this by using x cubed and x cubed. This x cubed times x cubed. This is where we'd add the exponents and get x to the 3 plus 3 is x to the 6th. Or you can think of it x to the power 3 times x to the power 3. We're multiplying it by itself, so we're squaring it. So x cubed squared, this is where we'd multiply exponents. X to the 3 times 2 is x to the 6. Whichever of those two ways makes more sense to you. So factoring, we've got x cubed times x cubed is x to the 6. 8x cubed, subtract 1x cubed is our 7x cubed, and 8 times negative 1 is negative 8. And set each factor equal to 0, solve for x.